Welcome back to G Fun Facts Online. Today, we are turning our gaze upward, away from our home planet, to a mystery that puzzled planetary scientists for decades. It is a story about a geological phenomenon with absolutely no equal on Earth. It involves a landscape that looks biological, a mechanism that acts like a pressure cooker, and a seasonal cycle so violent it transforms the surface of a planet every single year. We are talking about the Mars spiders. If you were to look at satellite imagery of the Martian South Pole, specifically around the high latitudes of 70 to 87 degrees south, you would see something that should be there. Amidst the ice and the red dust, there are sprawling black dendritic shapes. They have a central pit, and radiating out from that pit are dozens of spindly branching legs. They look exactly like spiders scurrying across the ice. These features, officially called araneiforms, range in size from tens of meters to a full kilometer across. And they don't just appear one by one, they swarm. They huddle together by the thousands, creating a texture that makes the skin of Mars look wrinkled, cracked, and strangely organic. For a long time, nobody knew what they were. Are they cracks? Are they signs of life? Are they fluid channels carved by water? It took a convergence of advanced orbital imaging, theoretical physics, and some incredibly difficult laboratory simulations on Earth to finally decipher the mechanism behind these alien sculptures. And the answer, as we found out, revealed a planetary process that is as violent as it is exotic. Today, we are going to explore the physics of the alien spring and the definitive solution to the riddle of the Mars spiders. The story of the Martian spiders begins in the late 1990s and early 2000s. This was the era of NASA's Mars Global Surveyor mission. As the surveyor began beaming back high-resolution images of the Martian surface, scientists noticed a stark difference between the north and south poles. The northern polar cap is relatively stable and rich in water ice, but the southern polar cap is a chaotic, shifting landscape. As the mission's cameras scanned the southern depths during the Martian winter, the area was shrouded in darkness. But as spring broke and the sun rose, the region transformed. Scientists called this the cryptic region or cryptic terrain. It earned this name because of a paradox in the thermal data. The region appeared cold, consistent with carbon dioxide ice, yet it looked dark, like bare soil. It had an unexplainable low reflectivity, or albedo. It was within this paradoxical zone that the images revealed these bizarre, fractal-like shapes etched into the surface. They looked like river tributaries or lightning strikes frozen in stone, but the visual resemblance to arachnids was undeniable. Consequently, araneiforms became the subject of intense speculation. The scientific community naturally hates a vacuum, so theories began to proliferate immediately. The first instinct was to look for Earth-like analogs. On Earth, dendritic or tree-like branching usually means fluid flow. Water carves channels that look just like these spiders. So the question arose, could there be liquid water beneath the South Pole? This was quickly dismissed. The temperatures in this region dropped to -130 degrees Celsius or lower. The atmospheric pressure is so thin that liquid water cannot exist in stable flows on the surface. It would instantly freeze or boil away. The next theory was volcanic fracturing. Some proposed that the spider legs were tension cracks formed by upwelling magma or tectonic stresses. But this didn't fit the data either. The radial symmetry of the spiders was too perfect, and the features were restricted only to this specific cryptic region of the South Pole. Tectonic features usually do not care about latitude or seasons, and of course, there were the biological misinterpretations. In the fringes of the internet and tabloid media, the Mars spiders became fuel for conspiracy theories. Much like the famous face on Mars from the Viking era, the spiders were claimed to be fossilized giant organisms, or even vegetation that bloomed in the Martian spring. While scientifically unfounded, these wild ideas highlighted just how desperate we were for a geological explanation that actually made sense. The breakthrough did not come from looking for Earth-like processes. It came from accepting that Mars is an alien world with alien chemistry. The key ingredient was carbon dioxide. To understand the spiders, you have to understand the atmosphere of Mars. Unlike Earth, where the atmosphere is nitrogen and oxygen, Mars is 95% carbon dioxide. During the harsh Martian winter, temperatures at the poles drop so low that the atmosphere itself freezes. About 30% of the entire planetary atmosphere deposits onto the polar caps as a layer of dry ice, or solid CO2, roughly 1 meter thick. This creates a seasonal ice cap that is not made of snow, but of a translucent, slab-like sheet of carbon dioxide. This slab is the canvas upon which the spiders are painted. In the early 2000s, a geophysicist named Kieffer proposed a radical hypothesis. He suggested that the spiders were not formed by liquid but by gas. His theory, now known as the Kieffer Model, described a solid-state greenhouse effect, a mechanism that has no natural occurrence on Earth. Let's break down the physics of this model, because it is fascinating. Imagine winter settles on the Martian South Pole. CO2 gas condenses into a slab of ice. Crucially, this ice is relatively transparent to visible sunlight, but opaque to thermal infrared radiation. It acts like a giant glass pane. When spring arrives, the sun penetrates this translucent ice slab and strikes the dark Martian soil, or regolith, underneath. The dark soil absorbs the sunlight and heats up. It tries to re-radiate this energy as heat, but the CO2 ice blocks this heat from escaping. The energy gets trapped at the base of the ice layer. This is the greenhouse trap. The trapped heat causes the CO2 ice at the very bottom of the slab to sublimate, meaning it turns directly from a solid into a gas, skipping the liquid phase entirely. This creates a growing pocket of high-pressure gas trapped between the heavy ice slab above and the soil below. As the pressure builds, the ice slab eventually cracks at its weakest point. The pressurized gas from the entire surrounding area rushes toward this vent at speeds reaching 160 kilometers per hour, or roughly 100 miles per hour. This is where the spider gets carved. As the gas rushes beneath the ice toward the vent, it scours the loose soil, carving deep radial channels. These channels become the legs of the spider. The gas then erupts out of the central crack, like a geyser, carrying dust and sand high into the Martian air. The dust then falls back downwind, creating dark fan-shaped deposits on top of the bright ice. These fans were the smoking gun that connected the spiders to the seasonal venting. The Kieffer model was elegant, but theoretical models need observational proof. The Mars Reconnaissance Orbiter, launched in 2005, provided exactly that. Its HiRISE camera, which is powerful enough to resolve features as small as a desk, monitored the cryptic terrain over several Martian years. They watched the spiders wake up. In early spring, the spiders were invisible, covered by the winter ice slab. Then, seemingly overnight, dark spots would appear. As spring progressed, these spots would grow into fans, oriented in the direction of the prevailing wind. Crucially, the spiders themselves, the etched troughs in the ground, were permanent geological scars. But the activity, the jetting gas and the dark fans, was seasonal. The spiders were the plumbing system, and the fans were the exhaust. Even with photographic evidence, there remained a significant hurdle. Geologists usually rely on comparative planetology. To understand a dune on Mars, they study a dune in the Sahara. But there is no place on Earth where CO2 freezes into translucent slabs and explodes. Attempting to prove the Kieffer model required recreating Mars in a lab. This posed immense engineering challenges. You need to reach temperatures of -140 degrees Celsius. You need a near vacuum, specifically about 6 millibars of pressure, which is less than 1% of Earth's sea level pressure. You need to account for Mars having only 1/3 of Earth's gravity, which affects how soil is lifted. And you need pure CO2 ice and a soil simulant that mimics the fineness of Martian dust. For years, experiments failed. Some couldn't get the pressure right. Others couldn't get the ice to form as a translucent slab. It often formed as snowy hoarfrost, which scatters light and breaks the greenhouse effect. The turning point came around 2020 and 2021, driven by researchers like Dr. Lauren McKeown at the Open University in the UK, and later Trinity College Dublin. They utilized a specialized Mars simulation chamber capable of holding the necessary vacuum and thermal conditions. Instead of trying to grow the ice from scratch, which is notoriously difficult to keep clear, they took a pragmatic approach. They drilled holes in blocks of dry ice and suspended them over beds of granular sediment. They then lowered the pressure to Martian levels and heated the substrate. The results were spectacular. The dry ice sublimated vigorously upon contact with the warm grains. The gas rushed through the pre-drilled vents. When they lifted the ice blocks, the sediment underneath had been scoured into perfect dendritic spider patterns. It was the first empirical evidence that the Kieffer model wasn't just good math, it was physical reality. The gas flow naturally self-organized into fractal channels, mimicking the exact morphology seen on Mars. But the confirmation journey didn't stop there. In 2024, NASA's Jet Propulsion Laboratory, or JPL, took the simulation a step further using their DUSTY testbed, which stands for Dirty Under Vacuum Simulation Testbed for Icy Environments. Researchers at JPL wanted to see if they could get the ice to crack naturally, rather than drilling a hole manually. They cooled a simulant soil, flooded the chamber with CO2 gas, and condensed it into a solid ice slab. Then they turned on a heater beneath the soil to simulate solar warming. This experiment yielded a surprise. The ice didn't just form on top of the soil, it formed within the pore spaces of the soil. When the sublimation began, it wasn't just gas rushing under the ice. The soil itself exploded from within. The pressure buildup caused the ice-soil mixture to fracture, shooting plumes of gas and debris into the chamber. This modification to the Kieffer model, where the spider is carved not just by surface scouring, but by the explosive fragmentation of frozen soil, helped explain some of the deeper, more rugged araneiforms that looked too substantial to be carved by gas wind alone. The success of the spider model unlocked a new understanding of an entire menagerie of features found in the Martian polar regions. Planetary scientists began to see the fingerprint of CO2 sublimation everywhere. They call this collection of features the Kieffer Zoo. First, there are the fried eggs. These are features consisting of a central broken terrain surrounded by a ring of lighter material. They are thought to be proto-spiders, or areas where the gas venting was less violent, lifting the ice slightly to deposit a halo of dust before settling back down. Then there is the laced terrain. In areas where the spiders are so dense they overlap, the ground takes on a textured, woven appearance. This represents a landscape that has been completely worked over by the sublimation process over thousands of years. We also see Dalmatian spots. Before the fans appear, the first sign of spring is often these dark blotches on the ice. These are the sites of the vertical jets. The gas blasts straight up, carrying dark sand. When the jet stops or the wind is low, the sand falls straight back down, creating a round spot. Finally, there is the Swiss cheese terrain. While spiders are constructive or erosional features in the soil, the Swiss cheese terrain is found in the permanent CO2 cap and consists of bizarre, flat-floored pits in the ice itself. These are caused by the sublimation of the ice cap year after year, where the sun burns holes into the CO2 layers, creating steep-walled depressions that grow and merge. The confirmation of the spider formation mechanism fundamentally changed our view of Mars. For a long time, Mars was viewed as a dead planet, a place where geology happened billions of years ago and then finished. The spiders prove that Mars is currently geologically active. It is not active with lava or tectonic plates, but with cryoventing. Every year, millions of tons of soil are moved, channels are deepened, and the landscape is reshaped. The south pole of Mars is a dynamic, shifting surface that is constantly being resculpted by the sun. This active erosion presents a puzzle. If spiders are carved every year, why aren't they miles deep? Why do they seem to preserve a specific size? The answer likely lies in the Martian dust cycle. While the spring vents scour the channels, the global dust storms of summer and autumn fill them back up. The spiders exist in a delicate equilibrium between being carved by gas and being buried by dust. This makes them excellent markers for climate stability. If the spiders are visible, it means the current climate regime has been stable for long enough to maintain them. Understanding araneiforms is also critical for future missions. A lander touching down in the cryptic region during early spring might find itself sitting on top of a geological time bomb. If a spacecraft's heat source warmed the ground beneath a CO2 slab, it could theoretically trigger an artificial jet, blasting the lander with high-velocity debris. Furthermore, the geyser-like plumes are sampling the subsurface for us. Instead of drilling, a future rover could potentially drive up to a fresh fan deposit and analyze the material that was just ejected from meters underground. It is nature's way of doing the excavation for us. The solution to the Araneiform mystery has opened the door to comparative cryomorphology. If CO2 jets can carve spiders on Mars, what about other icy worlds? When Voyager 2 flew past Neptune's moon Triton in 1989, it saw dark plumes erupting 8 kilometers into the sky. These are likely nitrogen geysers driven by a similar solid-state greenhouse effect. The sunlight warms the nitrogen ice, creating pressurized jets. We see similar physics potentially at play on Jupiter's moon, Europa, and even Pluto, where massive blades of ice are likely formed by sublimation. The Martian spiders are a testament to the power of scientific persistence. What started as a visual anomaly that evoked biological fears has transformed into a triumph of planetary physics. We now know that the spiders from Mars are the footprints of the sun, etched into the ground by the violent phase change of carbon dioxide. They remind us that the universe is not limited to the geological playbook of Earth. On a world where the air freezes and the ground explodes, the landscape takes on forms that are truly alien, yet perfectly understandable through the universal laws of physics. As we continue to gaze at the red planet, the spiders stand as a warning and an invitation. Expect the unexpected, for Mars is still alive in its own frozen, dusty way. Thank you for listening to Fun Facts Online.